Okay.
Please, chairs. My name is Maarten Honings, and I will introduce Georgina Lisasso, who will talk about pseudospectral methods for auralizations, and she will start where she used to be.
Okay. Well, good afternoon. Thank you for the introduction. It's a pleasure to be here. This talk is an invitation for different research teams concerned with working on auralizations to use the cast-based pseudospectral method. We propose to show that the pseudospectral method can be used to make auralizations simulating the input response of a room in a single run. Here is a diagram of the well-known auralization process. This is based on the obtaining the input response of an acoustic space. The geometric model requires several runs to compose the input response of a room. So, why? Acoustic properties of surfaces depends on frequencies. Also, the geometrical models require compute results for several frequencies bands and then combine them into a single input response. As in geometric models case, weight-based methods also require several runs to compose the input response of a room. But again, why? These methods solve differential equations by discretizing continuous variables. But in the math method, this results in unwanted numerical dispersion. To avoid numerical dispersion, the process must be applied for individual frequencies. Then, it's necessary to combine results for each frequency band into a single input response. In both models, to obtain the input response, the complex task of independently solving individual frequencies of narrow frequency bands is required to later be combined into the total input response. One of the main problems of numerical methods lays on the fact that differential equations solvers exhibit numerical dispersion resulting from length-wave discretization error. This in turn produces the unweighting and unphysical effect of propagation speed varying with the frequency. So, auralizations with the case-based pseudospectral method reduce or eliminate the problem of numerical dispersion. For example, this paper called Quantifying Numerical Errors in the Simulation of Transcranial Ultrasound Using Pseudospectral Methods states the problem as follows. Spectral methods are based on the principle that a solution can be obtained as the sum of certain basic functions, for example, sine functions, to then calculate suitable coefficients for the differential equation. They are closely related to finite elements. They are closely related to finite elements and finite difference time domain methods. The principal difference is that the spectral methods are basic functions that are solved for the whole domain, while for other method functions are solved across small subdomains. It could be argued that spectral methods use a global approach instead of a local approach. Here, pseudospectral methods replace the spatial gradient calculation by FDTD usually used in other methods with the Fourier collocation method. This, in itself, reduces the numerical dispersion for the spatial gradient, but not for the temporal gradient. Nonetheless, this can be correct for a homogeneous medium up to the Nyquist frequency employing a different operator. These aspects are sufficiently interesting to begin an exploratory analysis on pseudospectral method orient Auralizations based on producing a complete impulse response with a single simulation. Here I show you an impulse propagation in a three-dimensional space. This was defined for simulations with more than 60 million nodes in total, representing a cubic acoustic space. A spatial discretization resolution of 2 centimeters for each spatial dimension was defined. The center of the space is considered the coordinate origin all at 3 dimensions. Propagation of an impulse response was simulated for a free-field open acoustic space. The source was defined as a Dirichlet type source. This means that the source output is forced to have a time evolution that exactly matches the given signal, in this case an impulse. In this example, the source emits an impulse that propagates and is recorded by the sensor. As expected, the sensors record the impulse and reflections caused by the wall with its corresponding delay. Now, I will show you an example using this method to do Auralizations. The acoustic environment was a simple shoebox with one source and 2 sensors. The sensor was separate to hear the difference in the reverberant field. At first, we're going to listen the original file. It's not working. And now, the Auralization plane. Oh, it's not working. Well, I want to say thanks to my dog Draco for his contributions. Well, now let's listen to a more musical example. The configuration is the same as the previous example. Here we have a guitar sound. And now the Auralization. To conclude, results suggest that the cascade pseudospectral method may be suitable for using Auralizations. The principal advantages relies on the use of impulsive resources with broad range of frequencies. The tests carried out show that it is possible to obtain an impulse response in just one computation run. Different materials could be simulated based on density, propagation speed, and absorption to simulate wave propagation in more complex conditions. And finally, a greater exploration of method limitations must be carried out to verify if this does not hinder the advantage of simulating impulse on just one simulation run. This is all.
Georgina. Are there any questions?
The source in the shoebox, is it an was it an omnidirectional, or was it a source with a directivity towards?
No, it's a punctual source, only
monopole.
directional. Yeah.
Space lets to use another way of sources and dipole, for example, dipole, and different type of microphones too.
Mm-hmm.
Here was omnidirectional too.
Okay.
The source and the.
What we heard on the for the second receiver was like already having all the reflection from the box of wall. Right?
Yes, yes.
Yeah.
So in the shoebox you had the boundary, you had hard walls, I assume?
Yeah.
Rigid walls?
It's reflecting work.
So do you have ideas on how to make them like
Absorbing.
any arbitrary absorption or impedance?
Yeah, it's a part of future work. Analyze different conditions, boundaries.
But there's literature about that, huh? How you could do that.
Sorry?
I can send you, there's literature on how
Interesting, interesting. Thanks.
Okay, well, thank you.
The toolbox we use here is CowWeb. It's a open source toolbox for MATLAB and lets to modify the density of the material and the velocity. This is a way we can make absorbent materials in the walls.
You had you mentioned 60 million points.
Yeah.
So what computer did you run your simulation?
3 hours?
Computer times, you say?
No, and what like
An
hardware?
i7 3.4 gigahertz. It takes time.
Okay.
2 centimeters and 3 dimensions of some meters. Creo que después de eso. Bueno, okay.
Sorry.
Any more questions from the audience? If not, then thank you again.
Well,
And this was the last.